Welcome everybody to my talk. I've decided to call it a bird's eye view of a compiler, because we'll be kind of like a bird. My bird of choice is a goose. You'll see this all throughout the presentation. But it's a bird's eye view because it will be like flying above it from a distance, just looking at the components from like a high level. So we're not going to go into any nitty-gritty details. We'll just introduce a lot of concepts. We'll look at a piece of code that goes into a compiler, gets transformed, broken down, reshuffled, and then output as something else. And we'll see what each of those phases actually does. So if you are maybe a bit newer to development and not really thought about what a compiler does, I hope this talk will be perfect for you. Or if you're a seasoned veteran who's been developing all kinds of cool stuff for like years, but you still haven't thought much about what's going on inside of a compiler, I hope this will also bring something valuable to you. But the first thing I want to introduce is my face. My name is Joakim Lier. I stole that joke from Olafur. I love that guy. He does some great presentations. I'm sure you all saw the Doom in Space talk yesterday at the party. But I am a software engineer at Cisco, and I actually, well, at Cisco Norway, we make these video conferencing devices, and my role in that big machinery is maintaining our web browser. So that means I'm not a compiler engineer, I'm just an enthusiast. I really enjoy this kind of technology, and I like reading about it and playing with it in my spare time and doing all kinds of stuff with it. So, we only have 1 hour. We're gonna, like, the field of compiler construction and all the programming language theory it's just a huge topic. So we will have to do just the basics. We'll look at all kinds of different concepts, introduce them, illustrate them a little bit, and then move on. So we will not be diving into any more advanced topics, such as like optimization is a huge one. So we'll look at some examples maybe, but we won't really get into the details of when can we actually do this in practice. We'll just give you guys some terms and things you can follow up on if you feel like this is interesting. So now you have some words and you know how it fits into the pipeline, so you can possibly read about it by yourself later. So I'm just trying to create a little spark of interest if you guys realize, hey, this might be cool to learn more about. So that's my intention. And just to keep things simple, we'll assume that everything is ahead of time compiled, which is like the standard procedure for C and C++, where you insert your source code, compile it, and then later you do something with the output. In contrast to, for example, interpreted language, where it kind of does everything in one go, which is similar but has some differences, and we'll just ignore those. So compilers. My motivation to do this talk was after talking to some friends of mine who are also developers, and they told me, like, compilers, that's this black box. You don't really know what's going on, and it just makes programming work. And that kind of agitated me a little bit. So they were treating compilers like some sort of deep neural network, which is like, with its billions of parameters, it's impossible to reason with. But unlike some sort of deep neural network, a compiler is just a piece of software. If you have an open source compiler, you can just read the source code. You can reason about it. It might be an advanced piece of software, but it's still fully possible to reason about it and maybe even change it if you feel like something is off. But that doesn't really explain what the compiler does. So the core challenge is that your computer does not understand your code. If you do, I don't know, Java or C++ or C, your computer can't really comprehend that language. So you need something to translate your preferred language to something that the computer can use, right? So your computer only has some set of instructions, and that is not the same as your preferred programming language. So we have this notion of a source language, which is, for example, C++, whatever you want to write your code in, and then some target. That target can be many things. Just spoke of the instruction set, which is kind of a low-level concept, but it's also possible to have a compilation target be some high-level language. So, for example, TypeScript, if you're familiar, is a web language or language for web development, but it compiles down to JavaScript, which is another high-level language. And that works because the target language may have its set of tools that allows the computer to do something useful with it. And this is what keeps us from writing assembly all day long, because I kind of dare to say that most of us doesn't really write assembler code in our day-to-day jobs anymore, because we are able to build abstractions. We build C, so we can have structs, we can have functions, loops, all kind of good stuff to make us express ourselves. And that has been going on, giving us C++, giving us Java, giving us JavaScript, all kinds of different abstract languages that allow us to express ourselves in a very concise and neat manner. Also in our preferred way, because, you know, we have different preferences, and that's okay. But as always, since we're doing translation, we have to always make the right thing. We can't change anything, so we have to always stay correct, and that's, I think, the most important property of any compiler. Because if you write your piece of code and you compile it, and then it turns into something else, that compiler is not really worth anything, right? Because then it's just random or undefined, and we know what we think about undefined behavior in C++, so we wouldn't want every program to be undefined. That doesn't seem very productive. And of course, optimization is a big thing. It's kind of a weird thing, because if you were to build your own compiler, this is the only optional step. You don't need optimization, but it's probably the hardest and most actively researched part of a compiler, because you can do a lot of things, and nowadays we tend to assume all of our compilers are correct, and we rank them based on their efficiency or quality of code that they produce, or some other property like that. So it's an optional but very important step in a real production-grade compiler. So I've managed, or not managed, I decided to visualize this black box as something like this. And don't worry if you can't read all the text, it's just an illustration that shows us that we, from the top left here, have our input program. We break down the text, structure it somehow, transform it, and then produce some sort of artifact. That artifact can be many things, so I've just illustrated it using some representations of different kinds. So the structure of a compiler is mainly, at least the general sense of a compiler is generally split into three parts. These are connected by their outputs, and what I mean by that is the output of one part is the input of the next part, so it's a pipeline, just like a factory, right? And every part of the compiler has different considerations. So if you look at the table down here, we can see that the front end of the compiler is language specific, but it does not care about the target platform it's supposed to be running on, because it just deals with the specifics of the high-level language you are translating. The middle end, this is the front end, by the way, so the top part here. So we go from source code and we produce some structured data of some sort, oftentimes a tree, but we'll get back to that. The middle end takes that tree or structure and transforms it to something else. This is kind of the holy grail of computer science, because you're not really bound by language anymore, because we're just dealing with data structures. And we're not ready to produce any code yet, so we're not even platform dependent. So we just can do some pure computer science-y goodness, which I find to be really exciting. And finally, we have the back end, which takes the processed structures from the middle end and, if applicable, does some platform-specific transformations or optimizations, and finally generate our output code. And that obviously is platform-specific, because it's supposed to be running somewhere. And the neat part is that each of these three parts of a compiler is very distinct, and they have pretty nice interface in that the output is the next phase's input. So we can reuse our components. And that's the magic of LLVM, which has its own like textual format. So if you can read in your programming language and reduce it to that format, you can just leverage all of LLVM tools and get, I guess, some very advanced optimization for free. You don't really have to know about that. GCC kind of does the same. And by this I mean the GNU C compiler collection, not the C compiler, which includes several front ends which share the same, I guess, middle end, and then has several backends. So you can use the same machinery to process different languages for different platforms, which I think is a really neat property of dividing them up like this. But before we move on, we're supposed to be covering the front end right now. I just want to do a bit of theory first. Because I think it is very nice to express the syntax of a language, aka what you're writing, as a grammar. So I just want to freshen up grammars for everyone. So a language, as in the mathematical sense, is just all kinds of strings you're able to produce with some rules. And you have just a few symbols you can use. What that means is just it's a string rewriting system. So the grammars define rules, like you can see on the right-hand side here. So for example, the start string can be turned into a parenthesis. Semicolon just means that's the end of the production rule. In the bottom case here, we can see that a capital A can turn into a lowercase a and an uppercase a, or just a lowercase a, so we have a choice. And we have the notion of non-terminals and terminals. So I've used the convention of non-terminals being uppercase, and the non-terminals are the strings that you can't have in your final string. You have to keep processing them until you end up with only terminals, which in this case is the lowercase a and the literal parentheses open and close. There are many classes of languages and grammars, and I'm not going to get into that. I'll just say that context-free is a very good fit for programming languages. But you might have heard of regular languages or regular expressions, and this also fits into this description, but with some different properties. And a context-free grammar is a more expressive thing than a regular expression. So that's why I picked the grammar on the, what is it? Right-hand side for you guys. Because you can't recreate this using a regex. We'll see that a bit later. So you can use this grammar to both generate strings by just starting somewhere, for example, the start symbol by convention, and just applying rules arbitrarily until you get just terminals. On the flip side, you can take a string and apply the rules backwards and see if it makes sense. So I'll just run through a quick example. So we have the actions on this side and the states on the other side. So we start with the start symbol. I abbreviated parentheses to just paren. So we can apply this rule, which is this one up here, which leaves us with just a parenthesis symbol. Now we choose to apply this rule up here, which is that rule we can see, which just wraps it in the literal parenthesis signs. And we can do that twice. And now we're just generating, so I can do whatever, and if you guys want to do something else, that's also allowed. This is just up to choice, and this is an arbitrary choice. After wrapping it in parentheses 2 times, I choose to expand the parentheses into an A, because that's the alternative production we can use. So now our state looks like this. And now, I still have a non-terminal, that's the capital A. So I can choose between these two rules, and I choose to do first the topmost one, that leaves us with this, and then the bottom one, which leaves us with this, which is a string of only non-terminals. It's a perfectly valid string. It is part of the language, because we only follow the rules. And a regular expression can't do this, because this guarantees a balanced amount of opening and closing parentheses, and a regular expression can't count. That's the weakness. So this is why context-free languages are good for describing programming languages, because we do have a lot of matching brackets, like C is full of them, and just think about Lisp. But this isn't actually that useful. It's more useful to go the other way around, which is parsing, where we start with some string, and then we apply the rules backwards. So we have a lowercase a, and we see that we can collapse that into this non-terminal. So we do that. Now we're left in this state up here. And now we see that we have a lowercase a followed by the uppercase a, which looks like this rule up here. I mean down there. And then we just collapse that several times, and until we're just left with an a inside of parentheses. And we see that just an a can be collapsed into the parentheses non-terminal, which leaves us with this. And finally, we see that a parenthesized parenthesis can be collapsed into the parenthesis symbol, which finally leaves us to the start symbol. And that is kind of proof of this string being part of the language, because if you end up with a start symbol with no other symbols to spare, that's a successful parse. But there's a lot of more things to say about grammars. I will skip those, and if there's any clever people among you guys who have already read about grammars, you already know what I'm talking about. So programming languages, they're kind of just made up, right? I just write a document, a specification, and then I still don't have a programming language, because we need a compiler to implement that specification, right? Consider C++. We have a lot of specifications. Like every 3 years there's a big new one, and maybe more if for all I know. And these specifications aren't really real languages until they're implemented by compilers. And the special case about C++ is, the different compilers are implementing the specs at different paces. So we kind of have many different versions of C++, which are more or less compatible or incompatible, depends on the feature. But in defining the programming language, the syntax is, it's useful to define the syntax as a grammar, either explicitly or just sort of like an appendix, because it's a useful tool, where you just use a context-free one with some additions if there's any context-sensitive parts of the language. And this brings us to the front end, which is the first part I mentioned. So the front end is the only language-specific part. This is where you break down the input code, and you want to structure it somehow. So we break it down by extracting all the important bits we need, because there's a lot of syntactical elements to a programming language that's not necessarily required. It's just a syntax thing, right? And this is split up in two phases called lexing and parsing, or lexical analysis and syntax analysis if you're academic, I guess. We'll be covering syntax-directed translation later, and that ends up typically being an abstract syntax tree, which is a tree that represents the code you wrote according to the grammar rules we have. There's a very nice connection between the syntax tree and the grammar. It's kind of immediate sometimes. So, moving to the lexical analysis. This is where we ask ourselves, are the words we wrote in our programs correct? So it's kind of like, looking up in a dictionary. So we break down the string. In this case, it's a small C program where we make some assignment and then use printf. I'm not sure if you can see that, I'm sorry about that. But it's not that important. We just break it down to the smallest meaningful unit. And what that means is that every language has some reserved keywords, such as return or int, I guess, or if. And then we have like this recipe for how we can make an identifier. I think in C you can't have an identifier that starts with a number, for example. So you have like these rules that define how you make such an identifier. And then we have literals, like the number 2. That just means the number 2, right? So we have like our little system of dictionary lookups and some rules on how we should format some things. And then we just try to match all the different words we have in our program. For example, in this case, where we have like the int main function declaration, we see that int is the smallest useful piece of text because that's a built-in type. So that deserves its own little lexeme, which is a matched word. But the lexeme isn't that useful by itself, so you kind of categorize it. You say that, okay, the int is a built-in type or a reserved keyword. I'm actually not sure what it's defined as in C, but you get the idea. And that is the token. It's like categorized word. So by defining these rules and running through your program, you get this list of tokens. And this is what the parser needs to look at when we are trying to create the parse tree. Because then, by this point, we don't really want to be reading the text anymore. We want a generalized representation of the code, where an identifier is just an identifier. Because that makes our grammars work really nicely. Then we don't have to distinguish int main from type identifier. It's much more generalized. So we can match all kinds of function definitions that way. So the question we're asking ourselves is, does the sentence we read make any sense? Which means, is the order we're seeing these tokens correct? Which pretty much translates to verifying the grammatical rules, just like we did by hand a moment ago. And in English, this would look like, for example, if I said the sentence, I the can through, which really makes sense, right? But perhaps in German, but this is English, different grammars, right? In English, we would say, I threw the can, and that's a perfectly valid sentence. But I said that we were going from this list to a tree, and verifying rules doesn't really produce anything, right? So this brings us to the syntax-directed translation part. It's just a fancy way of saying we have our grammar, and we have some parser that checks that our grammar is withheld. And syntax-directed translation is about associating some kind of attribute, some data, to each of these production rules. And we call those semantic actions. So we're connecting our syntax, which is what we write, to the semantics, which is what we mean in some way, I guess. And we can use that to create the data structures as we go. So for each successful parse, we can, for example, create a node in a graph or a tree. And then when we parse the parent of that object, we can connect them, creating a tree as we go along. And we can also move the data up and down the tree, so we have it readily available wherever we want to. And then we can also prune the tree later, so it doesn't get as big. And if you write the parser yourself, you can just write your own code. But sometimes when I don't want to focus on the syntax, I use a parser generator, which can look something like this, where we have the well-known grammar rules. We've seen those before. And by the way, this is a grammar describing grammars, because I was trying to build my own parser generator, but I needed to parse a grammar. So kind of a meta thing, but don't worry about that. So this is just our pure old syntactical construct inside of a grammar. But this block right here is actual running C++ code with some additions to it. So this is from GNU Bison, which has this $sign notation, which just refers to the different part of the grammar rule above. So I say that when we successfully parse this thing, I want the $, which is the grammar rule, to become this C++ class I have created somewhere else. You can't see it, but trust me, it's there. And we can also index into the right-hand side using the dollars with numbers on them. It's one indexed for some reason. So 1 is the left-hand side. We skip the colon. It's just a syntactical thing. We don't need to keep it around. And finally, the $3 for the right-hand side. And now we have created a node. And maybe in some other grammatical rule, I connect this node to the rest of the tree. And so we can build up our parse tree. And a parse tree is something we call an intermediate representation. And this is where it starts getting very interesting, at least to me. So syntax is fun, but nowadays it's almost trivial, depending on the syntax. There are many tools you can use to make it a smooth experience, but IRs is much more up to you to define, to figure out what you want to use and how you want to use them. So an IR is just a representation of your code, just like the ASD we talked about, the syntax tree. That's just one kind of IR. And the point of an IR is looking at your code while highlighting some properties of it. So it's kind of, I like the glasses analogy. So like if you have some glasses that make you be nearsighted, you'll have a different view of the code than if you are farsighted. Or if you have blue glasses, then the colors will be different, so you can highlight different properties of your code. What this means is that you can use your data structures and some analysis to create another structure that describes, for example, the control flow of your program, which means when it's branching, so you can follow just the branches. You don't care about the individual statements anymore. You just want to look at where are the branches, how do they relate to each other, and when or if do they merge. And we have some other, what do you call it, a kind of a continuation of that, which is the dominator graph, which shows you what has to be done before the current block you're looking at. So it's building on top of each other. You can't really have a dominator tree without a control flow graph. You also have something called a three-address code, or a TAC. It's not an IR, it's just kind of a format of defining one. It just means that your expressions, I mean statements, have to be with only 3 things in it. So you have to break down a big compound expression, which makes it easier to reason about it, because when it's broken down, you can see all the sub-calculations and possibly do something smart about them. And finally, I just like putting up SSA, or static single assignment form. Yeah, I really enjoy that, but we'll look at that later, so I won't talk too much about it. And this is an important prerequisite. We need to have the notion of an IR and how we can analyze our data structures to convince ourselves that we can transform it into something else, and just keep doing that until we find the data we need. But we'll look at that in the middle end, which is right now, coincidentally. So, like I said, the middle end is both language and platform agnostic. You don't really care about those specifics. You're just bothered with your data structures, and you just want to analyze them and transform them, so you can learn as much as you can about the code as possible, which might enable optimization. But it's kind of like a forever going thing, because some transformations are just there. It's easy to do so, but others might require some analysis. But then if you do a transformation, that may enable more analysis or an optimization, which in itself is some sort of transformation. So you're always changing, which leads you to finding out that, okay, I did one analysis and I did this thing based off of that. But doing that thing enabled me to do a new analysis so I can do more stuff. So it just keeps on building on itself, which is really exciting. But this is where we have to be careful. Because remember what I said about always being correct. This is where we are really not allowed, but we have the opportunity to just change the program. And we don't really want to change the program if it changes the results, because then it's not the same program anymore. And if it's not the same program, your developer loses faith and nobody uses your compiler. So we can never change the results. That's super important. And changing something, as in an optimization or transformation, is always a trade-off. There's no such thing as an universally useful optimization. You're always optimizing for something. Maybe it's execution speed. But if you want faster execution speeds, you might have to introduce some complexity to your code, or maybe the code size increases. Or in any case, compilation is probably just going to take longer. So you have to pick and choose what you want to optimize for. You have to find the balance you're looking for, or maybe allow the user to tweak that using flags or something like that. And like I said, optimization may introduce artifacts, which leads you to having to do more analysis to maybe optimize away some optimization artifacts, so it keeps on building of itself. So yeah, I just want to make sure everyone knows that we can't change the program, because that's kind of like introducing nasal daemons to every single program ever, and as C++ programmers, we don't like that. So imagine this. You write this little C code. It's fairly simple. I hope you all understand that. You're just writing hello world and returning 0. So you build that and you run it. And I would be so pissed if this happened to me. Right? Because it's broken the contract. I said I wanted hello world and it didn't give me hello world. But maybe the compiler thought, okay, yeah, this guy, he wrote some code, used a function, didn't store the result, so he didn't need the function call, because the compiler forgot that side effects are, maybe a useful thing. Of course, this is a bad example and maybe more of a joke, but you get the idea. You have to be careful, because we really don't want this. So during in the middle end, when we do our analysis and transformations, we just ask questions about the code. Is this piece of code ever run? Is this variable what I think it is? Have you done this before? Or maybe do we even need to do this? And if you can find answer to these questions, then maybe you have found yourself an opportunity to optimize something. For example, if you see a piece of code that's never run, you can say it's dead and maybe remove it. If it's hard to know what value you're looking at, but you figure out a way to figure it out. Wait, that was a weird sentence. You figure out which value you're looking at, then maybe you found a way to simplify some sort of logic. And if you see something we've already done, maybe you can cache that result and reuse it, saving us some cycles of recomputing that value. So this has all been, very hand-wavy. So I told people I wouldn't use too much code in this presentation, but I just want to illustrate some optimizations. And I just want to make sure that everyone also understands that these are illustrations. Optimization is not done on text. We're not working with text when you optimize, but this is text just to illustrate. So the first two are called constant folding and propagation, which is something of like a basic optimization pretty much everyone does. But it's a good example of some optimization which is easy to reason about. So we have this program. We have a bunch of constants that have some values, but some of them require some computations. But the thing is, we don't need to emit code that does these computations, because they are constant, and this will never be anything different. So we can just do this compile time, saving the output program the work to do so. The same goes for C, where a times b is 45, and 90 divided by 2 is also 45. So we end up with something like this on the left-hand side. Left-hand side, yeah. So now we have C, which is also 0, so we know that. So we have done constant folding. That's the art of computing constant values during compile time. But notice that we're also returning 0 instead of C. That's the propagation part. We can rewrite some constant with its value, saving us a load, for example, which is, there's some gain to be had. Not the greatest one, but it's a nice optimization to know about. But again, we have to make sure we're allowed to do this, because otherwise we might break something. If these weren't constants, for example, if they were user input, we could never do this. And since we already have this nice piece of code, we also see that we don't really need the variables anymore. They're constant, but they don't change the program result. So that was our contract, right? We will never change the results of any program in any way. These constants does not change the result. So we can just remove them, which looks like this, which is some what am I looking for? Like it's a type of dead code elimination called a dead assignment elimination. So you make some value or constant and you're not using it, so you can safely remove it. Moving on is oh, sorry. Is I hate that name so much. It's too long. It's too verbose. But the thing is, you have a loop, and you have something that is invariant inside of the loop, which means it does not vary. It does not change. And then you code motion it out. You move it out. So you have a program like this. You always compute the number of total steps inside of the loop body. But that computation does not rely on anything that's changing inside of the loop. You just have these values up here. Those are the only dependencies. So what you really want to do is just move that out. It doesn't really, right? You see that? If you can prove that this is safe, this might actually save you a couple of cycles every single time that loop is rolling. And some loops are infinite, so that might save you a lot of time in the long run. And so when we have these total steps, it's finally computed, we know the value, and we use it in there. So what if I said, okay, but what if these guys are constant? Then we're able to do constant folding, which I just told you about, give us the value of this thing, compile time, and then we propagate it to this one over here, so we don't have the load. But then we don't really need the total steps variable at all anymore, so we can just remove it. So optimization enable more analysis, which may enable some more transformation, right? It kind of keeps on going, and you have to know when to stop. And I don't, so I did this. Another one which has a really easy base case, but is much harder to do in practice, is the loop unrolling. So doing a loop actually has some overhead. You have to do like the comparison, you have to increment the index. That is a small piece of work, but it's still work. So if you can prove to somehow that this will always be 10 iterations, you can just remove the loop and insert the loop body 10 times. Saves us the overhead of the loop, but will increase code size by quite a lot. So you have to know what you're optimizing for. Again, everything's a trade-off. And now, my favorite thing, or not favorite, but I enjoy it, the static single assignment form. So on the left-hand side, we have some little dumb program where we give A the value of 3, B something, then we reassign A and print it. And if we were trying to do something smart inside of this function called compile time, we would really have to know what value does A have. So we have to do some sort of data flow analysis, right? We have to figure out, okay, A used to be 3 at least. Let's see. Okay, yeah, there's a 5. Okay, so it's probably 5. And that's easy for us to see in the textual representation. But from a computer, a generalized algorithm, working with all sorts of programs, it might not be as easy. On the flip side, in SSA form, you can only instantiate the variable in one place and give it a value. Oh wait, yeah. You can only assign to a variable once. So if you ever do a reassignment such as this, it is in fact a new variable. So notice how we have A1 and A2 now. And when we look at the printf call, it's immediate which value we're looking at, because this A2, by the contract of being in an SSA form, has only one place it could have gotten its value. So now it's much easier to reason with. So this is not an optimization in itself, it just helps us analyze to figure out what to do next. But I feel like it's kind of interesting to see what happens when you have a branch. Because this is, I suppose, kind of specific to LLVM, but I thought it was a neat little trick. So we have this condition, which changes the value of A. And how do we express that in single static assignment form? We create our extra variables, just like before, and we give it some value based on the condition, right? But when we're supposed to return it, we need to know exactly which one to return. So we create a fourth A, which has something called a phi function in it. A phi function is not a real function, it is just a notation that tells us to, or tells the compiler rather, to insert code that gives us the value of the branch we took. So the result of a phi function, or the phi notation, is the branch we came from. Yeah? It's not specific to LLVM. I've just been working with LLVM lately, so I just made an assumption. But thank you. Okay, there you go. It is typically a common thing. Thank you. So yeah, I just thought it was a neat trick, and yeah, because the first time I looked at this and I did a conditional, I was like, wait, how do I know? Huh? You know, it's really hard to reason about, but this notation fixes that. So that was a bit of a transformation and optimization crash course, I guess, where we just illustrated a couple of things. So it's time to move on to the back end. So in the back end, we are doing everything platform specific, right? So if there are any platform specific optimizations we can do based on whatever platform we're targeting, we want to do them here. If there's no such thing, we can just move on to code generation, which of course is platform specific by nature. So we just take whatever IR we ended up in, or many of them, or some metadata from the middle end, and we use that to do some final optimization passes, and then code generation, finally. Oh boy, and I had a really hard time speaking generally about platform-specific analysis, because it's platform-specific. You can target whatever you want to, right? So you just have to know your platform. It's hard for me to give some specific guidelines in such a general manner, at least for me. But just keep in mind that the different platforms you can target may have such different behaviors, like the V8 engine of Chromium, the thing that runs JavaScript. It will behave completely different from like an embedded Raspberry Pi or an NVIDIA graphics card running CUDA. Yes. Their strengths and weaknesses are vastly different. Their mode of operation is just a whole, you know, it's different, which is what I'm trying to say. So you have to know about any well-performing patterns. If you're targeting some low-level construction, maybe you want to think about cache locality. I don't think you need to do that in the same, with the same amount of effort on something like the web, where you're going to be bound by internet latency, network latency. But on something like a Raspberry Pi or a graphics card, you really want to hit your cache locality. If you have a bunch of cache misses, then your program is going to perform bad, and your customers will be angry. Same goes for register allocation, which variables do you put in registers, and which do you spill out to the stack. It's just a lot of things to keep in mind, and those things you have to keep in mind changes per platform. So you have to be the expert here when you're writing a backend, which of course is great, because of the reusable components, we can leverage other people's backend if we did a good job making, for example, a middle end or a front end. So we can just mix and match as long as they're compatible. Which is why I found it to be interesting to learn LLVM, because I was up and running in almost no code at all. I just made a front end, and the LLVM project made everything else for me. Kind of a lazy man's approach, but it did work. Took me 5 days of not knowing what to do to a final product. So that was cool. And as always, we have to be conservative and careful because we can't change any results. I'm going to say this a lot of times, so you guys will never forget that, because you are now all aspiring compiler engineers and some professionals. Yeah, so we don't want to induce nasal demons in every single compiled program, because that's a very unpopular thing to do. Finally, code generation. This is the last step, so bear with me now. You've been great. We need to define some translation scheme, because all we have now is some data structures, right? It's not code, it's not text, it doesn't look like anything. So our translation scheme has to be both correct, because of nasal demons, right? And it has to take into the different considerations which we discussed for a platform. If it's instruction selection, which is the art of translating one instruction that maybe doesn't exist in the target language, so how would you translate that? And if you do that in a bad way, it's going to have different results, right? And yeah, you just have to really think about what's the feature set of my target, and how can I leverage that in a good way. So just think about assembly versus JavaScript, or a C compiler versus the TypeScript compiler. It's a world of difference. So again, we have some code. I hope you guys can read that. It's just an illustration of like a C++ program. You have an enumeration of some conference attendee, where someone has the conference pass, the workshop pass, the all access pass, there is a speaker. Then we have a class that's called a conference attendee, which can be constructed with a name and a type and printed nicely to the terminal somehow. And then in the main function, we just create one called Joakim, because I'm very inventive, and we print me. So we'll just use this to look at how can we map, for example, the class construct to different languages. And I realized after writing this that C++ classes is kind of a rabbit hole, because there's so much invisible going on. So we'll just simplify it, so don't hate me, okay? So how would we map the construct of a class to some different target? So I just done the exercise of lowering this code to some other languages. In JavaScript, classes is immediate, because we have the class keyword. We can just use that, and then that should be more or less the same thing. I'm not a JavaScript developer, but it was kind of interesting for me to see that enumerations weren't natively supported in JavaScript. So you have to actually figure out how to implement something like an enumeration by yourself in your compiler, and you have to stick with that. So that was, an interesting find, which kind of made me happy, because then someone has thought about that when they made TypeScript, which does support native enumerations. So this one is kind of given. It's more or less the same. But C, you need some sort of translation scheme, right? Because we don't have classes. And you have structs, which is kind of similar. It's some way to box together a bunch of values, right? But you can't associate member functions to it. So we can, with like some clever name scheming, we can emulate that by prefixing conference attendee before some functions that, for example, constructs a conference attendee or pretty prints it. And this will more or less give us something similar. So this is the kind of thing we have to think about. And I'm sure I've made a lot of mistakes in this, so just take it as an illustration, okay? Nice. And I'm just gonna do this. Okay, I'm not blue. So the next slide will maybe offend some people. And I realize that, so I apologize. Because C and JavaScript is one thing, but LLVMIR and assembly, I didn't want to write out the code, come on. Because assembly R kind of looks like some sort of assembly, except that it has user-defined types and function calls and a notion of something we can use as a variable. So it kind of looks like something similar to C. We would use the same approach, but it would look different because it's more assembly-like. On the assembly side, however, yeah, you guys know assembly. You have to think about how you want to lay out the structures in memory. You have to store that somehow so you can recall what's my name. You have to figure out how to get that, and you have to treat that as a unit, and then you can, fortunately, you have like the calling conventions, so you know how to make something that looks like a function, but there's a lot more thought that goes into it. So the lower abstraction level you're trying to target, the more thought you have to put into your translation scheme, because otherwise you're gonna have a bad time and not really be able to represent the code that was your input. So yeah, let's just not get into inheritance and that, because the code just blows up. It's a lot of things that's happening behind the scene. So with that said, I did like a test run for some friends with this presentation, and they were like, okay, this is cool. I learned a bunch of new stuff, but why do I need to learn this? So I figured I'd just make a slide about that. I feel like even if you're never going to touch the compiler source code in any shape or form, you're going to learn a couple of skills that you can transfer to a lot of stuff. I like developing developer tools or language tools. So if you can make a language front end, you can make syntax highlighting. You can make rules for formatters. And you know that little red line under your code in your editor when you've done something stupid? That's code analysis that you might have seen in, I guess, a combination of the front and middle end. So you can just use this outside of compilers to make all sorts of tools. And I think that's a really cool skill to have in your skill set, even though you're never going to actually make a compiler. So I figured it's worth learning. Plus, I think it's fun. I've never been paid to do this. I just do it for fun, pretty much. So yeah, thank you so much. And I just want to shout out that this is my first conference talk ever, so thank you for showing up. It made me really happy. So if there's any questions, I'm happy to take those, or at least try.